I'm going to talk about complex metallic alloys, but compared to the fascinating talk that preceded mine, it will be pretty simple. Thank you, Dr. Bosch. It was really beautiful. Um, this is the scope of my talk. I will briefly address the following points. What is a quasicrystal? What are different types of metallic quasicrystals? How were they discovered? From which alloys are they prepared? In brief, what is the most emblematic property of quasicrystals? What about surface energy and surface properties? And I will finish with few examples of applications based on surface properties and a brief conclusion. So everyone knows that in crystallography, it is fairly easy to cover a two-dimensional plane with squares or rectangles, with triangles or hexagons, but not with pentagons, regular pentagons. I mean, first, because you need two types of tiles, which brings you back to the rectangular tiling. And if you do this, you come to an impossibility, and this is a deep logical problem that was solved by a famous scientist now, Sir Roger Penrose, who received the Nobel Prize in physics for his work on black hole. But the way he solved this is too complex to go into details. I show you just few examples which are known as Penrose tilings. They all have this so-called forbidden five-fold symmetry, which you cannot find in two-dimensional tilings, and the equivalent in three dimensions, which is the icosahedral symmetry. This is another example of a five-fold tiling derived from Penrose tiling. So a number of people worked on solving the structure of these quasicrystals. I show you here only the result of a model that was built on a computer. There are only two types of atoms, blue and red. And you see, for instance, that red atoms are lying near a straight line or perpendicular to the screen, a plane. And you observe that there are two types of spacings between these planes, long L and short S. And I don't know if you can see it on my screen. It is hidden by something here. Okay, I need to move this. If I play a simple game, I iteratively generate a sequence of L and S. At one stage, I replace L by LS and S by L, and one stage after the other. I see this sequence, which is formed with no disorder, no ambiguity. One step defines entirely the next step. And at some stage, I have this sequence, which you have at the right bottom of the screen, LS, LL, and so on. And it is very easy to demonstrate that this sequence is necessarily aperiodic, and the ratio between S and L at some stage is just the golden mean. And you can observe the coincidence, at least locally, between this sequence here and the sequence of spacings between plane. And from that, you may infer that the sequence in the real material is also aperiodic. It's more complex than this, but I have no time to enter into details. So although it is not periodic, the sequence of red planes is fully determined by a non-ambiguous algorithm. There is no disorder, like in a crystal. The same holds true for any other plane, and as a consequence, diffraction patterns exhibit sharp diffraction spots like periodic crystals do. However, disorder may occur due to a specific mechanism called phason, which is a goldstone mode similar to phonons but in perpendicular space, but I have absolutely no time to go to this detail. So quasicrystals were found in metallic alloys, but also in polymers and oxide thin films, and I have no time to discuss this. And therefore, a quasicrystal is an ordered solid that must, not may, be described in a periodic frame of dimension higher than 3. And this is the difference between a quasicrystal and a normal crystal, as we all know, in solid condensate matter. So in metallic quasicrystals, there are essentially two types, one which is truly aperiodic in 3 dimensions, and another one which is called the icosahedral quasicrystal, and another one which is a periodic stacking along one direction of aperiodic layers of atoms, which is called the decagonal quasicrystal. And they were discovered by this gentleman, Danny Chestnut, when he was on a sabbatical in the United States. And this is what he observed after melt spinning aluminum manganese alloy in the electron microscope, a figure with sharp diffraction spots, which looks like a crystal, but which cannot be a normal crystal because it has clear fivefold symmetry along this direction. And if you look in all directions, you see that it has icosahedral point group symmetry. And after quite some time, but nevertheless, he was awarded the Nobel Prize in Chemistry for having forced the scientific community to change its paradigm about crystals. So this is a list of ternary systems in which stable quasicrystals have been found. The first one was aluminium, lithium, copper, which can be turned reversibly from liquid state to solid state with an icosahedral symmetry. And many others were discovered by a single gentleman who is Ampang Tsai in alloys like the ones which are marked with a yellow arrow on the screen. So this table shows you 2 examples of aluminum, palladium, manganese, and this series of atoms from the this row of manganese in the periodic table, and also aluminum, copper, iron, ruthenium, osmium. And you easily can observe that the third species does not mix with the second one. So you can form binary compounds with aluminum and palladium, or aluminum and one of these atoms, manganese, technetium, rhenium, but not between palladium and manganese. And of course, this is at the roots of the stability and formation of quasicrystals. Again, I have no time to go to this. I show you here the aluminum-rich corner of the aluminum, copper, iron system. Is 2 iron and copper form no compound, whereas they form compounds with the third one, aluminum. These compounds are shown here. And in the middle of this region is a crystal of containing a few tens of atoms, which is called the omega phase, with composition shown on the screen. And not far from this is found a quasicrystal, almost with the same composition, but definitely not exactly the same. And if I blow up this region here, I find a quasicrystal of icosahedral symmetry and a number of very complex crystals containing up to thousands of atoms per unit cell, with symmetry decaying down from icosahedral, high symmetry, to orthorhombic. Now, if I measure property, for instance, electrical resistivity in these compounds of the aluminum copper system. I see here a simple beta phase, which is CSCl type, 2 atoms per unit cell, which is characteristically a metal. The resistivity at low temperature is small, and it increases with increasing temperature. And if I increase the complexity of the unit cell, I see that the resistivity behavior reverts to that of, similar to that of a doped semiconductor. Low temperature resistivity is high, and the temperature coefficient of the resistivity is negative. And in fact, the conductivity changes from an Einstein type regime to a hopping mod type regime, depending on the size or number of atoms in the unit cell. So this is a very emblematic property of quasicrystals, which you find in all types of metallic quasicrystals known so far. Similarly, the optical conductivity changes with the complexity of the crystal. One which is essentially metallic shows the characteristic Drude peak, which is characteristic of a metal. And this Drude peak disappears when the complexity of the unit cell is large enough, and especially the red curve for an icosahedral quasicrystal. And this has a meaning, which is that the absorption of infrared light is very high. And I will show you an example later on of an application based on this property. And to finish with this emblematic property of quasicrystal, I show you here the density of states measured at the Fermi level as a function of the number of electrons per atoms or valence electrons, which is a mapping of the composition field. And you see a very deep decrease of the density of states due to the formation of a pseudo gap. So it's not a true gap like in a semiconductor, but almost a true gap, which is very deeply marked exactly at the composition of the quasicrystal, which we will exploit later on. So now let me come to surface properties. One typical is friction, which I can, for instance, measure using a pin on disc instrument housed in a vacuum chamber, like it is difficult to see on this figure. And if I evacuate the chamber down enough in pressure so that after a few rotations, the naked pin comes into contact with the naked sample when the native oxide has been removed by abrasion, I see this low friction of the quasicrystal. I'll show you in the next slide how different it is from normal, from conventional materials. But of course, if I reintroduce oxygen in the chamber, then tribooxidation plays the major role. So here are three friction tests made in these conditions. One with an oxide, alumina, one with hard steel, and the third one with a quasicrystal, icosahedral quasicrystal. Let's take the hard steel in contact with hard steel. You see that very soon after the beginning of the test, abrasion plays an important role, and in the end, the debris remain in the trace, so it's a pretty high friction. Alumina shows more or less the same behavior because of the transfer of steel from the indenter onto the trace, but the quasicrystal shows a markedly lower friction under vacuum. So this was studied by STM experiments and different theoretical approaches. It is not absolutely clear what is the dominant mechanism to explain why friction on a quasicrystal is significantly lower. One is most probably the incommensurability in the case of a periodic indent on a quasi-periodic sample, which decreases, of course, the friction. But another effect is shown here. You see that I can correct the friction from plowing and after measuring the hardness of the material, and adhesion term is remaining. And if I use different samples of different complexities, the resistivity of these materials increases from this to this, or the conductivity the other way around. And you see clearly that there is a correlation between the friction which is observed and the electronic conductivity, which is dominant for to understand the adhesion part of the friction. This is another example of friction as a function of hardness of the material. Of course, one expects that friction decreases with increasing hardness. This is the plowing component, which you can see on essentially aluminum, copper, iron samples, which do not produce much difference in density of states. But if I introduce chromium or other 3D metals, I will increase the contribution of these states at the Fermi energy, and the friction increases in proportion to the population of these states at the Fermi energy, which fits with the previous slide concerning electronic conductivity. So I can do this type of experiment with different materials of known surface energy and hardness, and with this calibrate the pin on disk device under vacuum, and using the same parameters with materials of unknown surface energy, I can correlate the friction to the surface energy and see that the friction, the surface energy of quasicrystalline materials is significantly below that of the constituents. For aluminum, copper, iron, it is found around 0.6 joule per square meter, to be compared to aluminum and copper and iron, which is about 4 times higher on normal, on crystalline pure iron. And this will be exploited later on. Of course, in literature, you find other approaches using more sophisticated ultra-high vacuum techniques, but they also give value for the surface energy, which is significantly below that of aluminum, which is the major constituent. Of course, in air, friction is hindered by the brittleness of quasicrystals, and it was not possible so far to use quasicrystals for any mechanical application because of this brittleness. But I show you here friction experiments which were performed in air on samples which were produced by as thick coatings by HVOF spraying using oxygen and kerosene. And using 2 different indenters, I show you here the friction coefficient, and the blue curve shows the change of the distance between indenter and surface in contact as a function of the distance run by the indenter in both cases. So you see here that the 2 surfaces come into contact. So this is the initial roughness that disappears, and essentially the distance does not change anymore. And in the same time, friction is extremely small for metallic systems in contact. It is of the order of 6%. I remind you the iron on iron experiment gives you 150%, which is much higher. And both experiments give a very, very small friction. Although the distance here is just 5 kilometers. So we stopped the experiment because it was lasting too long, but friction can be extremely low in these systems. Of course, the lubricant comes from the kerosene, and it is some ill-crystallized carbon that is trapped into the coating and which lubricates the friction. Now, surface wetting with different liquids is another property of interest. So this is a very simple experiment, at least in principle. You make a very small droplet on the surface and you measure the contact angle at equilibrium under the effect of the surface tensions of the liquid in contact with the solid in the presence of the vapor of the liquid. And from that you can derive the reversible adhesion energy of the liquid. And if you plot the cosine of this angle as a function of this term divided by the surface tension of the liquid, you expect that if the surface has no polar component, you will observe a straight line using several liquids of different polar and apolar components. And if the surface has a polar component, which is important in wetting, then of course the data points will come above this straight line. So this experiment was done using 5 different liquids. This one is water, the other ones, the names are too difficult to pronounce with my French accent, so I will not tell you, but these 2 are apolar liquids and these 3 are polar liquids. And with Teflon, which is a well-known apolar solid, you see indeed a straight line that extrapolates to -1. So this is typical for a surface that has no polar component. And in contrast, a single grain of an oxide, alumina here, you see for two non-polar liquids, okay, it goes to the straight line. But these 3 points are definitely above the line. And if I do the same measurement with a single grain of quasicrystal, although it is done in air, which means that the native alumina layer is covering the quasicrystal, I observe this straight line. So this means that the quasicrystal is typically apolar and has no polar component, in contrast to the oxide layer. And that was a big surprise. And furthermore, the reversible adhesion energy of water decreases with increasing thickness of the oxide layer until about 10 nanometers, and then you observe a reversal to the normal behavior. So this can be modeled. I will not go to the details of this model, but it is based on the formation of dipole images in the sea of Fermi electrons inside the quasicrystal under the oxide, which is just an inert spacing. And this interaction between dipoles on the water molecule and image dipoles determines the strength of this force, which must be included to reach equilibrium. And you can easily expect that because the quasicrystal has a much lower density of states than a normal metal like aluminum, this term will be minimized. Okay, I will not go into this. You will find references in my list of papers to read more about this. So a few examples of applications. One, of course, is an attempt to replace Teflon, which is soft and not thermally very stable, by a layer of quasicrystal, which is an hard material and can be warmed up above easily above 400 Celsius. That was one of my trials long time ago, and there are new attempts going on now in different countries. Another one is the solid-solid contact force measured under vacuum against different metals. I show you here classical metals, aluminum, copper, and hard steel, and two quasicrystals, which are of comparable hardness. This is the hardness. And this stick force, which can be measured by fretting experiments under high vacuum, shows you that these three hard metals have stick forces varying by about an order of magnitude between steel in contact with steel and steel in contact with a quasicrystal. And of course, this is reminiscent of aerospace applications and also applications in high vacuum technologies. This is a different experiment, which is the preparation of composite materials made of a blend between nylon and quasicrystalline powder, using a CO2 laser to melt locally the material to give the final shape of the material produced by additive manufacturing. And this is essentially infrared light. And with a quasicrystal, the absorption of light is much higher than with a conventional metal or metallic alloy. So the temperature of the grains locally increases in the conditions of this experiment by 40 K, which opens the process window very much. Instead of few degrees, you have few tenths of degrees. And with this, it is easy to produce composite materials. I show you here an example of something, a device which is used by Renault, the French car constructor, for race cars. These are exhaust pipes which are now in use on their cars. And this is based on the infrared absorption of the quasicrystal. Okay, I'm close to my conclusion. So there are many more phenomena. I was too short in time to go to the details. I show you just one example of a layer of lead atoms templated on a 5-fold surface of a quasicrystal. Again, you recognize the Penrose styling, which I've shown at the beginning. And when you do this, you create almost a real gap at the surface. So lead is becoming a superconductor when it abandons the classical periodicity to form a quasi-periodic layer. You can also use surfaces of quasicrystals to build artificial materials like what is shown here. These are fullerene balls, C60 balls on the surface of a quasicrystal. Again, you recognize here the Penrose tiling. And this artificial five-fold symmetric tiling is now under study to see which are the properties. Okay, I've finished. I give you here a list of papers for those who are interested to know more about these fascinating quasicrystals. I'm very grateful to my sponsors in Nancy in France and Ljubljana in Slovenia, especially CNRS, who paid me for about 40 years. This is, of course, a work that I did with many colleagues through the world, but especially these three ones. And I thank you for your attention. The address, the email address where you can write to me is given here, and on the first slide was my French address. Thank you for your attention, and thank you again for the invitation.